Stop worrying about homework and start learning with confidence. This is AskLearn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Two free body diagrams for two different parts of the problem. Here, the first part, we have a zero acceleration. So we can say for the first part, the acceleration is zero here. And so applying Newton's second law is a bit simple. We can say mg sine of theta minus the kinetic frictional force equaling mg sine of theta minus the coefficient of kinetic friction multiplied by the normal force. This is going to be equaling to the mass times the acceleration in the x direction. And in this case, this is equaling 0. We can also say mg cosine of theta minus the normal force equaling the mass times the acceleration in the y direction equaling 0. And so we can combine these two equations and find that the coefficient of kinetic friction is going to be equaling the tangent of the angle theta. Now for the second part of the problem, here the block is projected uphill. And in this case, the friction is always in the opposite direction of motion, where of course we have an initial velocity going up. However, our acceleration, because it's on an incline, it's most likely going to be down the incline. So we can say that here, applying Newton's second law for the uphill motion, we can say mg sine of theta plus the coefficient of kinetic friction equaling mg sine of theta plus the coefficient of kinetic friction multiplied by the normal force equaling the mass times the acceleration in the x direction. Mg cosine of theta minus the normal force equaling the mass times the acceleration in the y direction equaling 0. And so note we have that here the acceleration in the x direction will be greater than 0. However, it still means that the acceleration is downhill. Because we chose downhill to be positive. And so the speed of the block will decrease as it moves up the incline. And so for part A, we can say that using the coefficient of kinetic friction equaling tangent of the angle, and of course the normal force equaling mg cosine of theta, we can say then that the x component of the acceleration would be equaling to g sine of theta plus the coefficient of kinetic friction multiplied by the normal force divided by the mass m. And so this will be equaling to g sine of theta plus tangent of theta multiplied by mg cosine of theta. This will be divided by m, and then this will be equaling to simply 2g sine of theta. And so we can say that the distance block travels can be found using linear kinematics, where the velocity final squared equals the velocity initial squared plus 2 times, rather in this case, minus 2 times the acceleration in the x direction multiplied by delta x. And so to find delta x, this would be equaling to the initial velocity squared, given that the final velocity is 0. This will be divided by 2 times the acceleration in the x direction. This is equaling the initial velocity squared divided by 4g sine of theta. And so this would be our answer for part A. For part B, we know that almost always the coefficient of static friction is going to be greater than the coefficient of kinetic friction. And so the angle of repose, this would of course be the angle of repose, the minimum angle necessary for a stationary block to start sliding downhill. That's the definition of the angle of. You can say that the coefficient of static friction is going to be equaling tangent of theta, the angle of repose. And so we expect that here the angle of repose is going to be greater than the angle found in part A. And so when the block comes to rest, the incline is actually not steep enough to cause it from slipping down the incline again. So we can say when the block comes to rest, we can say it stays at rest. That is the end of the solution. Thank you for watching.